So how well does something dissolve in what, Alyssa? All this water. This is all about water and nothing else, which is fine because water is pretty much everywhere, right? So it makes sense to just worry about how well something dissolves in water. I mean, our bodies are pretty much all water. So whether it's a drug system or trying to get taste on your tongue, man, pretty much everything needs to dissolve in water. And if it doesn't dissolve at all, you'd have something like a lava lamp, right? There'd be nothing that they don't mix at all. So we've got, oh, here's an example of what we're trying to do or not, right? Because here I have water, I have solid in it. Is this the system we're talking about? In other words, do you have to have a bunch of solid on the bottom to solve these solubility problems? Andrea, what do you think? Do you have to have the solid on the bottom? Right? Could I just have had the same amount of water and then take a little bit of the solid and dip it in there and see if it dissolves or not? Yeah, maybe. Okay, so the type of questions we're talking about have to be equilibrium. That means you have to have the solid there. It has to be, it's the S word, Kenneth. Has to be saturated, right? Well, soluble too, right? Has to be saturated. And it's not going to be much of a question if our solid has what cations in it. What were they? They're always 100% soluble. Alkali metals. Lithium, pick your anion. Sodium, pick your anion. Potassium, pick your anion. It's always going to dissolve 100%. There's no question. There's nothing to calculate. We got to mess with, we have calculations for what's the concentration that actually dissolved, how much dissolved for something like this, I don't know, calcium phosphate, right? I mean, it doesn't, it makes it precipitate. But some of that breaks into solution, just a little tiny bit. How much? That's the calculation. And that's pretty much how all these bloody drugs are that you take. You can only metabolize about, I don't know, 8% maximum. Usually it's a lot less. So it's a real solubility problem to see what your dosage is of these, you know, prescription drugs or whatever the heck people are taking. So if it's not very soluble at all, you end up with these solubility tables. They call them KSP, equilibrium constants. And I'll just give you a hint. The bigger K is, the more soluble, the more it will dissolve and break into its ions. So if you're looking at that table, let's just see if we're reading it right. Steph, which compound, which solid dissolves the most in water? Which compound is the most soluble? Magnesium hydroxide. She says magnesium hydroxide has 10. Magnesium oxalate has a 10 to the negative 5. So can you find anybody find a number bigger than 10 to the negative 5? Silver acetate. 10 to the negative 3? Ooh, that's pretty dang big. Are there any other 10 to the negative 3s? Mm-mm. Yeah, so that would be the most soluble. Where'd it go? Silver. There it is, acetate. There it is. That's the one that's the most soluble. And in fact, if you remember, you don't really know how we're going to solve these yet, but I'll give you a hint. You don't want to have this as a homework question. Silver acetate is the system, because that KSP is so big, we're not going to be able to drop any X's. So you don't want to see that in a homework problem or a quiz question. You have to do a full quadratic. Anyway, but look, at most everything else is extremely small. So odds are we won't be doing any full quadratics. In fact, I don't think there is any homework that does. But notice how we've got a table, and again, we've got an equilibrium constant with subscripts, SP. So that means you have to write the equilibrium that reaction in a certain way. But before we write that reaction, Kendall, what do you think SP stands for?
Solubility product.
Perfect. Solubility product. Okay, so we want to write the solubility product for this. I'm just making up this solid. Remember, the first guy is always the cation. Second is always the anion. All right? And remember how this works? Like the little 2 Bowdy is the charge on the Y, and the 3, everybody's the charge on the X. Okay, so now that you can read this, Mia, what side do you write the solid on? The reactant or the product side? The reactant side, because you want it to break up to its ions. And the bigger the equilibrium constant is, the more ions you have. So that you got to put the solid over here. X2, Y3 with a big S on it. Okay. Then the reactants, Kenneth, would be X positive. X positive 3. Keep going. Plus Y negative 2. It's close. What's he missing? Yeah. Because we've got how many X's? 2 of them, so we better, how we balance this, Alyssa? There you go. Complete. Okay. Okay. So that's the general idea. How do you write all KSP reactions? So we have to remember that. It's just like, how do you write a Ka reaction? How do you write a Kb reaction? Now you have to know how to write a KSP reaction. If you don't write it in this format, all your answers, all your work is just a waste of time, because that's how the Ks are formatted. Okay, Megan, we've got barium phosphate, slightly soluble in water. How would you write the solubility reaction, the KSP reaction for barium phosphate? Perfect. Keep going.
Plus 2PO4 -2.
Excellent. Now she's going to lose a point.
The solubility on
The S subscript. There you go. We should be writing what subscripts down here to get brownie points? AQs. All right, dissolved, because it's soluble, dissolved in water. Okay. Write the equilibrium constant expression Andromeda, the KSP expression. So there's our reaction. KSP equals what over what? The BA plus 2. Now, what are you doing with that 3?
Oh, 3 is the exponent.
The exponent. And then we were supposed to write it in what?
Brackets.
Brackets. Okay, good. Keep going.
And the PO4 negative 3. With 2.
Yep.
Over 1.
Perfect. She caught it. Solids, you don't show up. Equilibrium constants. Okay. So that's kind of where we're heading. Now the homework, it would be nice if they quit there, but you can't. Doesn't do anybody any good just to write that kind of stuff. You can't make any predictions. What we want to do is, what's the solubility for any solid? Now I changed this a little bit, but the same thing you have in your notes. How do you calculate the solubility of any solid in water? In other words, what will be the concentration of barium in the water? What will be the concentration of phosphate in the water? What will be the concentration of ibuprofen in your blood, right? So how do you get, and that's the technical jargon though is solubility. So how do you calculate the solubility in water for this stuff? So our game plan. Andrea, let's see if you can make a good guess here. Solubility is the same as the blank in, is the same as the X in blank for a KSP reaction. same as x in blank. Where did we use x? Yeah, when have we been, what's this x coming from? Yeah, but when did we ever use x? We're writing a reaction. Ice table, right? So you're writing a reaction, then you have to make this ice table, right? I should probably have the word table after this. The x in a ice table. Okay, for a KSP reaction. Now, to make this work, Cameron, all the measurements in that ice table have to be in units of... Man, don't buy a lottery ticket today, dude. Concentration. Everything has to be in units of concentration. Otherwise, this is not going to work. Okay, so we've got the game plan. The game plan is you get a question like this. What's the solubility? And then, well, that means just remember, it's the X in ice. Well, if you have ice, you have to have a reaction, and that's going to be the KSP reaction. So, Jose, let's start then with a KSP reaction for this thing, because they want to know what the solubility is. CaF2. Yeah.
Ca plus 2 and F.
With the subscript down here is just 1. So this will be minus 1. Yep. Okay. Keep going. You got to balance it yet, though.
And 2.
Yeah. Yeah. So 2 in front of the F. Perfect. There it is. There's our KSP reaction. Oh, we should write solid. I forgot. Okay. We're supposed to do ice, though. So, Alyssa, I, C, E. How would you fill this out? Yeah, so we could just write what? Well, I think what, yeah, question mark. What, before I even think about anything, I do the easy stuff. What could you put down the column for that entire solid column? Slashes or dashes, right? Because you know it never shows up. So that's the first thing I do. Whenever I see solids and liquids, and then I start doing stuff. And remember what they're saying. What they're saying is this, you have to picture this. This is the only way I can figure this out. You have this pure water, and then you dump in a heck of a lot of calcium fluoride. A lot, so that it's sitting down there. And you wait a month. Whatever, you know what I mean? You probably don't have to wait a month, but a month is guaranteed, right? You wait a month, you come back, you make sure that there is at least still some solid on the bottom. That's the solution you're worried about. So when we say initial, we have to be talking about initial calcium ion or initial fluoride ion. So your initial was just this pure water. So there isn't any. So we can just put what in there for the initials? Dashes or zeros, whatever you like. Right? There isn't anything there. And then what do we put in the change row, everybody? Plus x and plus 2x. So we end up with just x and 2x. Okay. Now look what's coming up, though. Look at C. All right? Now you've got something to put in the initial row. So realize the difference in how the English of these things. The English, when they say it's just, oh, it's just in water, there's no initial. But when they say, oh, it's in, there's your common ion. Then you have something to put in the initial row. Anyway, let's finish this. So we've got find the solubility in water. Okay, so we've got our ice table. Steph, now what would you do? Yeah, right, that KSP reaction thing. So my KSP is equal to 3.4 times 10 to the negative 11. And Steph, that's going to be what over what? What's on top? Concentration of Well, if you do, I would write the expression because you guys haven't done this very often. On top is going to be products over reactants. So Ca, good. Ca, because if you haven't done, this is the first time especially, I wouldn't skip any steps. Because you could jump into doing the x's what you were doing, but let's not screw up. Ca plus 2 and then, and that one squared, all over 1, right? So we have 3.4 times 10 to the negative 11. Now I think it's easier to put in the x's. What would you put in here, Kendall? The calcium concentration is x. Yeah. So you see the kind of the little insurance policy there? By writing this first step, it didn't take very long, but you sure won't screw up in this step then. Okay, so we've got 3.4 times 10 to the negative 11, Audrey, is really equal to what? How would you simplify that part?
Multiply both sides by 1 to get the 1, right?
Oh, yeah. Yeah, we can get rid of that. But how are you going to simplify x times 2x squared? What is that going to be? Yeah, distribute. Distribute that x and the 2x squared. What would you end up with? Right? So this first part, 2x quantity squared would be 4x squared, right? So 4x squared and then times x, 4x cubed, right? That should be 4x cubed. And you're right, the one doesn't do anything, so just really 4x cubed. All right, everybody with me so far? Okay, Bowdy. Find the solubility. So all we got to do is find out what x is, give our answer, and we're done. So how are you going to solve for x? Divide by 4, and then take the cube root. And on this calculator, Bowdy, where is the cube root? Over the plus minus sign. Yeah, there it is. To the 1/3. Okay. You could also raise it, push the xy, and take it to the point 333. So let's try it, see if you get it. (3.4 times 10 to the negative 11 divided by 4, hit equals, take the cube root, about 2.04 times 10 to the negative 4. Did you get it, Mia? 2.04 times 10 to the negative 4 is what I got. Make sure you can get that to work. So now's the time to get all this calculator issue out of the way. Okay. So you don't want to lose silly points though, Kenneth. Because if you just write that answer, ooh, it's mathematically correct, but you don't have any units. What units do you have to put on that? Big M, very good, because this is a concentration table. It's an ice table, but it's in units of concentration, so it's big M. In fact, it's really big M of what? Calcium fluoride, right? Or you can kind of think of it this way. X is the concentration of calcium. Take x times 2, that's going to be the concentration of fluoride, F minus. So, but they want the solubility in part B. The homework likes to ask this. They want the units in grams per liter. So how you do this, you do 2.04 times 10 to the negative 4. And Kenneth said it was big M. And big M is what over what? Moles over liters. Okay, so the liters part looks good. But, Megan, we got to convert those moles into grams, right? So the question really is, moles of what? So then we can put that compound here and put it down there. You find the molar mass. Moles of what? CaF2, right? Because they want to know the solubility of CaF2. So X is CaF2 in concentration, big M. So we got a calcium, a couple fluorides. What is that? I can't read that. 2 times fluorine's around 19. So around 78.1 or so grams. That's the molar mass of calcium fluoride. You get about 0.016 grams of calcium fluoride per liter. Oh, 0.016, not 0.16. That's what I got. Did you get that?
Oh, yeah, I got it.
Okay. Okay. So Andrea, look at this part. And this is just typical homework, what's coming. And then they have you go through all this work, and then they change the question. Find the solubility of calcium fluoride in 0.1 molar sodium fluoride in units of grams per liter. What would you do? They want solubility, so solubility is the ice table. You got to do it all again. But what changes? The initial concentration. You put this 0.1 under the what? Under the F minus. Now, do you multiply it by 2? Do you multiply it by 2? Because in your, you have 2 F's here. No. No, don't do it. The initial concentration of F is 0.1. Right? So try it again. Okay, now before you go through all this work and try it again, will your answer, because this is a quick check, will your answer be bigger, smaller, or the same as 0.016? Because now you have an initial amount. Think of the, what's that guy's name? The French guy, the chandelier? His principle? Le Chatelier? Le Chatelier, right? We are now adding a reactant or product. We're adding a product. We have too much product. Equilibrium has to shift towards reactants, shift back to the solid. So this number better go down. We've got a lot less now because we screwed it up. So whatever you get, it better be smaller than 0.016 or you screwed up.
So that number is bigger.
This is, yeah, whatever number we get is going to be smaller than this. It has to be. That's Le Chatelier's principle. The solubility went down because of the common ion effect, with the technical jargon. So try it again. See what you get. Do the exact same thing, except now you've got something to plug in the initial row. And then you get to play the game of dropping the x. So you don't have to do a full quadratic. So try it. And then we'll go to the boards and finish out the day. Have some fun. Have some real fun.
How do you get this number again?
Okay, what I would put this in there first.
Yeah.
Okay, divide by 4 and have it equals.
Oh,
Divide by 4, then hit equals. There you go. So you need that. You have to hit equals first, and then you have to take the cube root on both sides. And that's that thing right there. So shift.
Oh, okay. I kind of got it, but like I was.
Yeah, you got it now.
Sir, seeing E, what do I put? It's just
So it's always the change. So the change is
plus 2.
2x, yeah?
2x. Oh, so.
And then so it's going to be, it's always add up the initial and the change, you get the final.
Okay, I was just making sure it's still 2x then.
Yeah? 0.1.
Oh, yeah. Thank you.
Uh-huh.
So, am I putting the 0.1
For right down here, exactly.
Okay, so there's two of these.
It doesn't matter. It's the initial concentration of F. That 2, the only place that 2 matters is you have a 2x in the change row, and it also becomes that coefficient in this. Comes the comes the exponent. Right? And you add them up to get the equilibrium row. So 0 plus x, that's going to be x. This will be 0.1 plus 2x. And then you plug it all into your KSP expression. So it should be a real similar problem. In fact, this one I think is probably going to be easier. It's a little bit easier, I think. The math is easier.
Okay. So since you have to square all of this.
Now remember though, it's 10 to the negative 11. So it's really going to be x times, you have 0.1 plus 2x here, not 4x.
Wait.
You said 2x, right? 2x.
See, because I was
0.1 plus 2x, quantity squared.
Yeah, like
Right, exactly, right here. So what you got to do is you recognize, x is going to be really, really small. So if x is really, really small, multiply it by 2, it's still really, really small.
Yeah.
Add it to 0.1, I get 0.1. So that's going to be 0.1 squared. Don't forget to still square it, though.
So, okay, so the top is just going to be 0.1 squared.
Well, don't forget your x. You got your first x in there. X times 0.1 squared. So I think this step is the real trick to that question, right? Make sure that you recognize, 10 to the negative 11. So whenever I'm adding or subtracting x, I can drop that. You have to be adding or subtracting. You can't drop this one. Because you multiply by a small number, that's huge. You're going to get a huge difference. But if you add or subtract a really small number, you get the same result. So just don't forget to square that 0.1 also, because that doesn't go away. So 0.1 plus 2x is really just 0.1. Remember how we dropped that? Because we look at this, and it's 10 to the negative, I think 10 to the negative 4 was questionable, but 10 to the negative 5, 10 to the negative 6, 10 to the negative 7, it's great. You can drop those. So the math, I think these common ion effect problems are called, I think the math is a lot easier. We don't even have to look, just divide this by 0.1 squared, you have your answer. The math is easier. what was it? 78.1 is the molar mass of calcium fluoride. 2.6 times 10 to the negative 7. So did you get around 2.6 times 10 to the negative 7 grams per liter? Audrey did. Kenneth did. Definitely smaller than 0.016, so it's on the right track. Should be right. Okay. So let's. Do you want to go to the boards? Bobby? Want to go to the boards? You guys really don't like that? I thought you did.
Yeah, sometimes. On Wednesdays. On a Wednesday, yeah.
Fine. Fine. Solubility of magnesium oxalate is 0.0093. Calculate the KSP. Oh, yeah. The solubility of magnesium oxalate in water is 0.093. Find KSP. This is really different, Andrea, than it's a twist. They want us to calculate that K number. Yeah, usually you can just look them up in the table. So whatever we calculate, hopefully we get what's in the table. But how would you do this? Work backwards, exactly. I would set up that ice table. And when you set up the ice table, now you know what what's that 0.0093? That's the what in the ice table? That's the X. Make that ice table. You know what X is. No lottery tickets today. That's your X. See if you can get it. So write out the KSP reaction, do ice, set up your KSP expression. Plug in what X is, and you'll have it. Right? Set up the KSP reaction, do ice, just like always, except now you know what X is, so it's a lot easier. So, but then you didn't put it in over here.
Oh, I didn't.
So what I would do is I would just do the ice table like regular. You do X and 2X, X and 2X. Set up the KSP expression, all in terms of X and 2X. And then you substitute in. Otherwise, it gets kind of confusing. Because you forget to substitute here and don't here. I mean, you're halfway there, but I think it'd be cleaner. So it'd be cleaner, I think, if you make the ice table just all with X's. Don't put any numbers in there. Just put it all with X's. Write the KSP expression, all with X's. And substitute in what X is, the 0.093, substitute that as the very last step. Oh, this is an uncommon ion. I can see the confusion. Oxalate. Oxalate is C2O4 with a what charge? -2. And I know that because magnesium has a +2. Right? Good. So that goes into oxalate and magnesium. So your KSP is just what? What expression? X squared. All over 1. So it looked like a complicated question, but it ends up being pretty straightforward in the end. So what do you put in for x? 0.0093. Not bad at all. So I got about 8.6 times 10 to the negative 5. So if you got it, try the next one. Yeah, because they wanted to know what the KSP is. Oh, there's no units on KSP. What do I have a big M there for? Right? Just habit, trying to get solubility all the time. That doesn't make any sense. Equilibrium constants don't have units. That's an analytical chemistry problem, question. Mm-hmm.
Yeah, this there'll only be X's too since it's bromate and
Yeah. Yeah, I got to make these more difficult, don't I?
Put the 3 in front.
Yes. Oh, except the units are messed up.
Oh, because it's in grams.
Yeah, so all you got to do is convert that to, yes, and then you do the exact same thing. Do you catch what Andrea's talking about for 29? Just exact same thing, just change what to what? Grams to moles. Yeah, those grams per liter is messed up. Then it'll be the exact same problem. Well, you're going to have to convert it, right? Get that whole x expression again, and then substitute it in your x, but it has to be in moles per liter, not grams per liter. What did you get?
well, I think we have this, but I'm not sure. What we have here, since we have grams, we don't have the grams for the actual full acid.
This is what helps to me is write G and then an L. G and then, well, no, the L goes on the bottom, right? So the G has, yeah, and this is moles.
Okay, already.
Moles.
I already like the whole thing. I just
Yeah,
wanted to make sure.
exactly. So it's going to have to, a silver, a bromine, and 3 oxygens has to go down there. 9.3 times 10 to the negative 10. Anybody else get 9.3 times 10 to the negative 10?
Yeah.
The final answer?
Okay.
Great. So final answer, 9.3 times 10 to the negative 10. 2 people got that. So no. Oh, I was going to tell you.